Alright, so today I'm going to be explaining another important paper with the title Learning How to Propagate Messages in Graph Neural Networks. This KDD paper in 2021. This paper studies the problem of learning message propagation strategies for graph neural networks. One of the challenges for graph neural network is that of defining the propagation strategy. For instance, the choices of propagation steps are often specialized to a single graph and are not personalized to different nodes. To compensate this for this, in this paper we present learning to propagate, a general learning framework that not only learns the GNN parameters for prediction, but more importantly can explicitly learn the interpretable and personalized propagate strategies for different nodes and various types of web graphs. We introduce the optimal propagation steps as latent variables to help find the maximum likelihood estimation of the GNN parameters in a variational expectation maximization framework. This is an illustration of the needing for personalized propagation. The color, for example, green, gray, and yellow, denotes the class of the node. White nodes denote the unlabeled nodes. So in graph neural network, we do aggregation and update in the message passing. But here we introduce the learning to propagate, which can perform personalized message passing for better node representation learning and a more interpretable prediction process. The key idea is to introduce a discrete latent variable t sub n for each node v sub n, which denotes the personalized optimal propagation step of v sub n. How to learn t sub n is challenging given no explicit supervision on the optimal propagation step of v sub n. So we propose a generative model for modeling the joint distribution of node labels and propagation steps conditioned on the node attributes and graphs. For example, we want to learn this probability, and formulate the learning to propagate framework as a variational objective. We consider designing process of graph neural networks as follows. We first choose the number of propagation layers for all nodes and the types of aggregation function parameterized by theta. Then for each training label of node n, we typically conduct maximum likelihood estimation of the marginal likelihood over the observed labels. So this is predicted probability of node y sub n having label y sub n using h sub kn, and h is a node representation of node v sub n after stacking k propagation steps. Specifically for each node v sub n, we introduce a latent discrete variable t sub n to denote the optimal propagation step, where k is the predefined maximum step, and t sub n can be 0, which corresponds to use non-aggregated features for prediction. We allow t sub n to be 0 because for some nodes in heterophilic graphs, the neighborhood information is noisy. Aggregating the neighborhood information may result in worse performance. T sub n is node-wise because the optimal propagation step for each node may vary largely from one node to another. Latent variable t sub n, we propose the following generative model with modeling the joint distribution of each observed label and latent t sub n. So this is the prior of propagation variable, and theta is the parameter shared by all nodes. This one, p sub theta of y sub n, is just a label prediction probability. Since we do not have any prior how to propagate, P of t sub n is just 1 over k plus 1, just uniform distribution. Now, learning the parameter of theta of GNN by maximizing this likelihood helps make label prediction in the testing phase. Finally, we do inferring the following posterior of the latent variable. But there are many challenges. We cannot directly learn the parameter theta since it involves marginalizing latent variable, which is generally time-consuming and intractable. To solve the challenges, we adopt the variational inference principle and instead consider the following lower bound. So we consider lower bound, and now we have this one that you are familiar with. This is maximizing the elbow is equivalent to maximizing is equation 5. And make variational distribution, which is Q. This one is the approximation of the true distribution. Now, learning to select. In variational inference principle, we can introduce a variational distribution. However, we cannot fit each Q individually by solving n times k parameters, which increases overfitting risk given the limited labels. So we consider amortization inference, which avoids the optimization of the parameters v sub n for each local variational distribution. Instead, it fits a shared neural network to calculate each to calculate each local variable v sub n. So here wk is just trainable learnable transformation, and h is representation of node at kth layer, and phi here is just set of parameters. This is illustration. The vanilla GNN is A. This is just a vanilla GNN, but B predicts the selected probability over all propagation steps. And C forces each node to personally quit its propagation process. It reminds me the stopping diffusion in diffusion-based graph generation, because there they have such a technique that they understand when to quit, when to stop. So learning to quit is important. Instead of directly modeling the selection probability over every propagation step, we can model the probability of existing propagation process and transform the modeling of multinomial probability parameters into the modeling of the logits of binomial probability parameters. So we consider modeling the quit probability at each layer for each node n. So alpha is just the probability that node v sub n quits propagating at kth layer. And maximizing elbow 7 is challenging, and the lack of labels for test data further exacerbates the difficulty. So we propose the alternate expectation maximization. So minimizing of the negative elbow can be solved by the expectation maximization algorithm. However, we cannot utilize the non-parametric posterior since label is not available for test nodes. We need to let the training and testing pipeline be consistent. So we consider projecting a non-parametric posterior to parametric posterior. We adopt an approximation which has also been used in classic vague sleep algorithm by minimizing the forward KL divergence. Then we can get the following pseudo-maximizing likelihood. So we minimize the following negative elbow with reparametrization trick. Now here T hat, this T hat is drawn from a categorical distribution with a discrete variational distribution. And the Gumbel softmax distribution is smooth so that phi can be optimized by standard backpropagation. This Gumbel softmax, we use it in several papers. It's a good trick if you have problem of discontinuity when you want to do conventional backpropagation. So it's a trick to handle and smooth it. So the introduced inference framework network for joint learning also increases the risk of overfitting. So they use this trick of train and validation to avoid it, using bi-level optimization. I mean, posing the problem as a bi-level objective. Otherwise, this is very straightforward. So we update lower level and then update upper level. Research question 5 says that could the proposed framework effectively the personalized and interpretive propagation strategies for each node? And we study the propagation strategy for individual nodes. So this observation matches our intuition that different nodes need different propagation strategies, and the prediction of a node will be confused if it has too many propagation steps, and thus cannot benefit much from message propagation. This is a summary of results on homophily graphs. You know, Quora, CiteSeer, PubMed are homophily graphs. But a little bit heterophily graphs are like Actor or Texas. But still, these have many homophily.